there's no deep learning here, right? This is just setting up well-posedness, and that we can actually restrict to some smaller space of constraints. Now we're going to go over into the deep learning portion. So the way that we're approaching this is by taking the mean field FBSDE that we had at the start, or sorry, the Mikhine-Vlasov FBSDE that we had at the start, which we posit is part of the statement of the problem, and we discretize it. So here, little h, there might be a bit of confusion. Little h is, say, delta t. That's the time steps that you use, and this is your classic Euler discretization, where we replace the law by the empirical distribution. And the way that this works is we're trying to find this object here and the initial condition for y. So we posit that there is a neural net parametrization for those two objects that accepts the states and the state and the adjoint in the case of z, and those get transformed into some control that we then use in this forward equation. You posit that, you push it forward through this MVFBSDE forward in time, really, and then you look at the error that you get at the terminal condition, and you try to minimize this error by seeking over those two neural net parametrizations. This is almost a direct generalization of the deep BSDE approach. Except here now, again, you have the law of these processes showing up in the forward equation and then the backward equation in general. So we'd like to prove something about this system, about this methodology, that it does indeed converge to the true solution. And we've gotten, we were quite lucky, in fact, that there is already some result out there by Christoph Reisinger and his group, which illustrates that the error, if I discretize such a problem and use a policy that is parametrized by these neural nets here, you can show that the error between the solution that you would get from this approximation and the true solutions, it's going to be bounded above by this type of error. Now, there's a few different terms in there, so let's just dissect the important ones. This here is related to the modulus of continuity of the various drift coefficients that show up, drift and diffusive coefficients that show up in the MVFBSDE. This error here is related to the difference between the solution at discrete points and the solution on the entire time domain. For well-behaved drifts and diffusive coefficients, this error term is really kind of like delta t. And then this error term here is the error between the terminal condition that you're trying to attain and the one that you do attain by approximation with the neural net. So that's a very nice result. It doesn't quite give us the solution to our problem, because our problem is not just the solution to the MVFBSDE. It's really the solution to the principal agent game, which part of it is solved by solving an MVFBSDE in order to solve the Nash equilibria portion of the problem, but it doesn't solve the principles portion. So for that, we then have to go on and prove that if we do this discretization and get this discrete solution that are parametrized by these neural nets and optimize within a subset of the full optimization problem, that the error between the true solution and this is in fact bounded by this squared epsilon. And what is the squared epsilon? Well, it's related to the error term that we saw above. And you can, there are universal approximation theorems that are going to tell you something about the control of this error. So for that, we can go back to the DPSDE paper in order to provide some additional bounds on that. But we've basically stopped here. Otherwise, it's just error bounds on top of error bounds on top of error bounds, and you just get lost, right? You have to stop somewhere. So that more or less, I think, summarizes all of the key theoretical contributions from the piece. This part is not, by the way, all of these convergence results, we have not posted this yet. All that we've posted with respect to the PAMFG is the methodology, the setup of the problem, and so on. We're writing this part up right now. So how does it look in terms of implementation? So in terms of implementation, the idea here is, so there's a lot of different pieces going on here. I'm going to try to zero in your focus. Let's look in here for a moment. What we do is, as we've demonstrated, if you're going to try to solve the problem on the full convex functions in this space that we call the G beta A comma B, if instead we say approximate that by piecewise linear functions, say if we're thinking of a one-dimensional case, you just take put options and you add them up together with different weights that are all positive. This will ensure that you have something that's convex. You can also add call type payoffs at a particular point. So we get this kind of, I'm not drawing that very well. These type of shapes, and you can smoothen out what's going on at these kinks in order to make sure that you are in fact in C11 bounded by beta. That's going to provide us with a subspace over which we optimize. And once we're trying to optimize within that subspace, we say we pick one function. Now go ahead and solve the Nash equilibria with Clarion condition. How do we do that? Well, you do that by solving the MVFBSDE. What does that involve? Well, that involves iterating and reducing. Let me go back to here. Nope. Where is it? I went back too far. There we go. So once you've picked a particular G, your goal is basically to minimize this loss by varying the network parameters that show up here and here. And you do this using, any classic method that you'd find in PyTorch, right? You've parameterized it, so then you use gradient descent of some sort. That's what this inner loop is doing. You fix the outer, where we have this approximation of what the penalty will be. Then once you've found that Nash equilibria by solving that MVFBSDE with the Clarion conditions, you estimate the loss associated with that particular function. And then you might think, okay, now what do? You go out and you do a gradient step for this function, this penalty function. Well, you could, that's what you'd like to do, but how do you get an estimate of the gradient correctly there? So the way that we do this is, let me think of it like that. This is a particular G, right? So we're at some point in the space of coefficients that tell us the slopes at each one of these piecewise linear parts. And what we'll do is we create a little epsilon ball around that slope, sample a few more points there. And for each one of those, we solve for the Nash equilibria with the Clarion condition, which means solve the MVFBSDE. We get an estimate of the loss at each one of those points, and then we estimate another neural net on top of that to be able to compute a gradient. There's quite a few moving pieces there. So that's what the next parts do. They say, okay, once you're at a point in this convex function space that you've approximated by these piecewise linears, let's sample around there to get new estimates of the loss in a region around where you currently are, so that now we can compute a more efficient gradient in the direction of the penalty function itself. Right? So there's two levels of optimizations that are going on, right? And then we iterate that. That's what this methodology is describing here. So I'm going to show you an example of this. What you have here is the case where we've just run it with, I think, 10 or 20 knot points for this piecewise linear function. And we've solved exactly that problem that I set up as the example problem in the very beginning. This rec market where you're trading recs, you are generating or renting potential capacity and expanding your own capacity. And of course, price is endogenized. And this